Welcome to Politically Incorrect course on machine learning, part 3. In the last part, we spoke about all the tools that we use in this world. We spoke about many things that have, as we saw, complicated names, but at the end, you saw that many of those are actually stuff that we learned in high school, really. And then I don't know why they make it so complicated, but now we'll see that all that stuff is crap, basically. That's why this is a politically incorrect course. And then we will see that all this stuff can be replaced by a magical new tool that I'm really stoked on, and you will see why. For example, see this, I'll draw a simulation here in chess and between chess and Go. You see chess at the top and Go at the bottom. Go is it's a board game very common in China that is considered the hardest one because, as you can see from chess and Go, with chess for each movement you have another 35 possible movements. With Go, that number goes to 250. So you may remember that more or less 20 years ago, IBM had this computer called Deep Blue, which was able to match Garry Kasparov, and then who was the world champion, using regular AI techniques such as the ones we saw. However, it was impossible to beat someone at Go, and then the computers will reach a level of 5, and apparently the highest level in Go is 9, so they couldn't go beyond that until they decided to use this new thing called neural networks. And then back in 2014 and in 2017, AlphaGo Master, which was the neural network they developed, beat 3 times this guy called KG and took a $1.5 million prize from Google. So it was proven that neural networks were the way to go. And then, hold on. So we have a new name here called deep learning. Before we had machine learning, and then but we have a new name called deep learning. As you remember, machine learning is a subset of AI, which basically uses data as a source of input. With deep learning is a subset of machine learning, which basically uses only one tool, which is neural networks. And a very simple comparison. We have an input, how to say, a picture of a car or something, and then with regular machine learning, in this case, in this picture, a decision tree, you may remember what it is, I hope you do. Then you do all kinds of if-thens or something possibilities until you decide that it's a car. With deep learning is a different thing, and then as you can see, you have all these balls interconnected, etc., until you have the same result. So what's an artificial neural network? It's one of the main tools that we are using today. And then the name neural means because it mimics the brain. That's supposed to, we'll see that yes it does, but no it does not. So it's one of these corny names at the end. It doesn't really mimic the brain, but we'll say that it does. They are not new. They were invented back in 1940. So again, the same question: why only now? Yeah, because we didn't have computers enough, powerful enough at the time to how to say for that thing. Also, because at that time we didn't have a magic tool called backpropagation, which I will explain at the end of this presentation. And then which is actually the tool that allows these systems to learn. Otherwise they always produce the same result, and if the result is no good, then it's pointless. So right now, what I will do is at playground.tensorflow.org, there is one that is pretty visual that we can play with. Let me see if I can get this thing to work here. So you can see. Okay. You might be seeing this, hope you do. You see that we have things like epoch, learning rate, activation, problem type. This is looks complicated, but at the end it is not really. This is a classification problem. Remember, we have classification and regression. We'll do just classification. The idea is for the computer to figure it out that these are blue balls and these are orange balls. For us it's easy, but for a computer it's not. Here you have features, okay, which is basically pieces of images. You can choose more if you want. And you have layers hidden. We'll explain what that is. You can add more layers, for example, or something. Or you can add neurons here, or you can add etc. We'll start with a simple thing. We'll choose Sigmoid as an activation, and you will see that makes a lot of difference. Okay. The idea again is for this thingy to be able to identify blue balls here, and how to say, and orange balls here. So you're using the activation Sigmoid, learning rate of 0.03. We'll see that if we change this, they make a lot of difference. See, that is actually getting a result. Finally, how to say, he learned that he was able to differentiate these blue balls here. Okay, so we'll now change from Sigmoid to Relu. Okay, we'll reload this stuff and you'll see what happens. Okay, basically that's it. So you see that it was much faster in finding the result if we change this activation thingy from Sigmoid to Relu. Okay, now I'll change this from 0.03 to 1, for example, and we'll try again with Relu. Oh, wow, big difference. See? Now we'll try with linear, same thing again, and we seem to be getting nowhere. Over here you see the lines that connect these neurons things, and you see that some are thicker than the others because the thick ones have a bigger weight. Okay, some of these neurons are not even being used apparently, or have a weight that is zero. So by now you figure it out that apparently what makes a difference is the learning rate and the activation. And also we can, okay, so what happens if we stick a bunch of layers, okay, and a bunch of neurons? We'll see that if it makes a difference. Remember that we tried with, with activation linear and learning rate 1. We'll try again. Apparently this is going nowhere. Okay, we saw that this linear thing doesn't work, but Relu seems to be cool, so we'll try with the Relu. Again, it doesn't seem to go anywhere. So we'll try 10, which is also cool, that also works pretty well. Many times even better than Relu. Okay, apparently it would almost found out the answer, and then it got lost. So you see that many times the idea of, oh, let's stick as many layers and neurons as we can think of, that doesn't work out. Okay. So back to where we were. So we already saw that neural networks work like brain. And I'm a biologist, so I remember an analogy between a neuron. As you know, then a neuron is this basic cell of the brain, and a toilet that I learned in college. Because a toilet has some principles that are also used by neurons that, how to say, for example, an action potential. When you flush, an impulse is sent down the sewer pipe. Like a neuron, a toilet needs to reload. A toilet needs to reload the water tank. Neuron also, they cannot fire. They need to reload chemically. It has, and an important thing is that, and we'll see this plays a major role, that always flushes with the same intensity. I mean, it doesn't matter how hard you press on the thingy, you will get the same amount of water. Neurons work like that. So you can think of neural networks basically as millions of toilets interconnected. Again, this is a politically incorrect course, so you get the idea. A major difference though. In the image you saw that a brain neuron always fires with the same intensity. That's the big difference between a brain neuron and a computer neuron. Because a brain neuron, it just sends a 0 or a nothing. And whereas a computer neuron sends values with different numbers. You remember that some of those lines were thicker than the other. That's because of the weight. Okay, we will see what a weight is. So I would think that if we really change this idea of sending different values to just sending zeros and ones, to really, in a way, to really make this binary, I think that could hold the answer to deeper learning. That's my opinion. So basically, we have 3 neural networks. And then again, and I'll repeat again, why are we studying neural networks? Because you will see that once you go neural network, it's like heroin. Once you try heroin, you don't care about food, you don't care about sex, you don't care about the sun, family, etc. You just want more heroin. Same thing with this neural networks thing. Once you go into this stuff, you're like, why did I study all that stuff, decision trees and KD means, all that garbage, if I can just do this, use this for anything that I think. And they're actually more powerful, as we already saw with the IBM and the Go thing. My point. So that's why I decided to make an entire presentation just for neural networks, because once you go neural network, believe me, you will never want to go back to all the garbage we learned in the other video. So again, we have 3 kinds of neural networks: ANN, which is artificial, or DNN, which is deep neural networks. The difference is we say that is deep when we have, this will be an ANN and this will be a DNN. Basically, if we have a lot of these layers called hidden layers, we'll study them, then we call it deep. Otherwise, it's just ANN, artificial neural network. So ANN or DNN is just the neural network that we use for everyday purposes. Okay. CNN, it's not the TV thing. It's convolutional neural network. These are used for processing images. I plan to do an entire presentation on this because this is complicated, and because this is actually what we do at Tech and Trash. So this is what I do best. So that hopefully will be the last installment of this amazing series. So basically a convolution, just to give you an idea, see how we have a picture of a car, and then we take a chunk of this picture, and we take a chunk of that picture and a chunk of that picture, etc. It works of convolutions, which is it is a mathematical equation that basically simplifies things. Okay. So CNNs are used for images. Okay, that's the kind of stuff you would use for face identification, for example. RNN is recurrent neural networks. Those are used mainly for language recognition, audio, financial markets, and anything that is linear and needs to have a memory on the, how to say, on all the history. The problem with the neural networks is each one of these layers, they don't keep a history on the data they have processed. They just get the data from this guy. Okay, this guy gets the data from this guy, who gets the data from this guy, etc. They just pass the data along, end of story. With our RNN, you see that, how to say, there is a feed forward thing that, how to say, that allows them to keep a kind of memory. Okay. So again, these are used for data that if you work with recognition of text, you will use yes or RNN, or with an audio, or with a stock market thing. So the components of a neural networks are many. The first is the inputs. Here we have a simple one, and we have two things: feed forward and backpropagation. Feed forward is when we get the data, we send it over the nodes. These balls are nodes, and then, or neurons, and then we send them to, how to say, and we send them to as many neurons as possible until we have one or more outputs. So basically, inputs is the data we want to process. We can have as many as we want here. A layer can be an input layer, an output layer, or a hidden layer. The ones in the middle are what's called hidden. We already saw that we can have as many as we want. However, at the end, as you saw, it's just a waste of money and time because they don't really do any good. So so you will ask, okay, so how many layers and how many neurons do we make? That's actually an art and a science, and then we'll see that there are some, how to say, rules of thumb. Okay. Each neuron is basically an equation of three numbers: an input, a weight, and a bias, and finally all of them squashed by an activation function. Remember the activation function that we saw in the demo that I did? Remember Sigmoid, 10, and ReLU? We will study this with more detail. And remember that they played a major role. Okay. The connections are basically what these lines connecting the different neurons. Not much to be learned here. A weight is a very important thing and is part of the mathematical equation. Remember that a neuron is basically a mathematical equation between three numbers: an input, a weight, and a bias, all of them finally squashed by an activation function. So a weight is one of these numbers that are processed by neurons and get updated by this backpropagation. See, backpropagation thing I will explain later. A bias is also another number processed, again updated by backpropagation. We will study each one of these in detail. Activation function, well, we already saw that they play a major role, and then they squash the numbers will within a specific range. Otherwise, each one of these guys, this will have 1 million, this will have minus 10, this one would have 1 gazillion, this one would be 0, this will be chaotic. Okay, so the activation function is what basically keeps this stuff at bay and this whole thing into something manageable. Okay, backpropagation again is what the function that goes back, updating all this weight, bias, and it's actually the technique that allows these neural networks to learn. Remember that I said that the first neural networks did not have this wonderful thing. So once you would give an input and the output would be always the same, so they would not learn. So if the output was no good, well, you're screwed. And basically output is the result that we want. within. Remember that we are always doing statistics, so this is not 2 plus 2. Okay, it could be, the result could be 3.9, 4.1, etc. Neurons and layers. We already saw that we can have as many neurons and layers as we want, but it gets to a point in which it's kind of dumb to put more, because like you saw, they make no difference, or even just make this system go berserk and it doesn't produce any result. Another important thing, and this is very important to mention, is that if you put too many neurons, not layers, neurons, you will end up with overfeeding. The problem is that at the end, each one of these neurons, they kind of learn, which is kind of weird, because I said that they do not, but in a way they can. Remember that I said that only RNNs is neural networks in which each neuron has a memory, remember, and then that's why they are used for audio and stuff, audio and stock markets and text recognition, etc. Well, at the end, these neurons kind of learn, and the problem is that if you have too many of them, they start to act like a memory bank, and at the end you have overfeeding, which is I think I already explained this, and I'll explain it again because it's a common problem, and it's worse than underfeeding. Underfeeding is when you have an improperly trained model. It's bad. But overfeeding is even worse, in which you have a model that is way too smart. It's basically a model that is only able to understand its own data set. Basically memorize its data set, and is able to identify the data set with 100% precision, and you're like, wow, I rock and roll. No, you don't. How to say, if you have 100% precision, most likely you are overfeeding. As simple as that. So basically, if you give the system new data, you will realize that it's unable to identify anything because it's stuck to its own data. So basically, there are 3 rules of thumbs on the number of hidden neurons. The first is the number of hidden neurons should be between the size of the input layer and the size of the output layer. The number of hidden neurons should be 2/3 the size of the input layer plus the size of the output layer. Or the number of hidden neurons should be less than twice the size of the input layer. By now you figured it out that each one has a personal taste. This is like cooking, okay? Some like more salt, others like less salt. At the end, you decide which works best for you, and you develop your own salty cuisine or not, okay? Again, this is how, this is how things, neuron works. It takes an input, multiplies by the neuron's weight. After it has done all these multiplications for all the neurons here, it has, for each one, it gets the weight multiplies by the, by the input, and finally gets all this stuff, okay, all this multiplication of weights by the data that it got from each one of these guys. After it finishes all this stuff, it adds a bias, okay, and then we'll see which each one of these in detail. It finally gets this result, this number, feeds it to activation function, which squashes the number within a reasonable rate. Otherwise, each one of these guys, this guy will say that would have 1 million. This other guy, hold on, this guy will have a number of 2. This guy will have a number of 1 minus 1 trillion, or this guy, etc. Okay, so. And finally, after you squashed this number by the activation function, you send it to the next layer or to the output layer. So we spoke a lot about weights, and they are very valuable, and major thing in this. Remember that the lines at that simulation thing, some were thin and some were thick. That's because of the weights. So how neural networks work? I mean, where are these weights calculated? Where do they come from? First, the system just generates some bullshit weights. 1, 2, 3, 1 million, whatever. Okay, random numbers. As you can imagine, at the end it generates a result which is also bullshit. But then backpropagation takes place and sends it all back saying, no, hold on, this is way too far from what I was expecting. Let's try with these other numbers, these weights of, instead of 1 million, let's put 500,000. And then again, it generates a new number, and no, it's still far off, not so much now, let's try it again. Instead of 500,000, let's try 50. Oh, now it's working. So basically, the way that works is first we create some bullshit weights. We see the result's not good, then we adjust the weights until we get a result which is as close as possible. A bias is just like a weight. The only difference, like I said, is that the weights are multiplied, each one for each particular neuron in that layer, where a bias is like a weight, but it's just it gets added at the end at the end of that equation. So again, we get each one of these guys, different weight, multiplied, add all this stuff, and after we add it, we add the bias, which is again works like a weight. We start with a bullshit number, we add etc. Backpropagation sends it back, say no, this is no good, try again, and we and then and at the end, the bias is an important thing because it determines if a neuron will fire or not. We will see that in this sense, these neural networks work much like a brain. Remember that I said that in a neuron, in an organic neuron, a brain fires or not. Then these neurons work like that as well. And it is the bias at the end which kind of determines if a neuron will fire or not. And it's a kind of a cheat code. Basically, if you don't have bias, the numbers are, even with the weights, etc., they're still too far off. So the bias gives again a meaning. It puts everything into some kind of sense. Okay. So again, we saw the activation functions. They squash these numbers into ranges that could be from 0 to 1, -1 to 1, -1 to 0. They usually go to within that range, okay? But in ranges which are always the same, okay? Otherwise, again, each neuron will have, in a layer, one would have a value of 1 million, the other guy has a value of 2, the other guy has a value of -1 gazillion, and it's a total chaos, okay? So, there are many activation functions. Each day a new one is found, etc. And if you want to look cool, in your company, you can say, we are using this activation function, which was at least covered yesterday by some major scholar at Google or something, etc. Okay. The only thing is that you'll see that all these funky new activation functions, they are not encoded in the softwares that you use. We covered Keras, TF-Learn, even TensorFlow. So many times you have to actually create code extra in those systems in order to be able to use this new thing that you just found out in some Google thing, in some website you found. So the first one was Sigmoid. Remember Sigmoid that kind of sucked? Well, that's pretty much. However, it works, but it takes long. Remember, then it squashes the result from 0 and 1. If you like graphs, I hate these things. You can see them here. See that 0 or 1. So anything. It's always between these numbers. It can be 0, 0.1, 0.2, 0.66667, 0. Blah 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 until 0.9999992 until 1. As simple as that. ReLU is the main thing. I would say basically squashes it between anything from 0 to top. Okay, over here. It works like, how to say, like Sigmoid, but over here you see that is, how to say, that is linear. That creates a problem called dead ReLU, which happens that if too many values in the network are 0, and then at this point some of these neurons will never fire anymore, and you have the half dead brain, because half of these neurons are dead and will never wake up, and they're just laying there doing nothing. So we have a variant called leaky ReLU. This is actually pretty used in images and then image recognition. You see that it allows for a little bit of minus. Over here is always 0, end of story. We will never get below 0. Over here, a little bit, it's allowed. So yeah, it's a little bit more flexible than ReLU, I guess. 10 is, again, ReLU, remember that this is the best, okay? So either this or this, okay? This, go for this, especially leaky ReLU, and stay there. Another activation function is 10, which is a hyperbolic tangent. Is similar to Sigmoid, but more steep than, how to say, this mouse thing that works. And but it has a difference. It squashes the result from -1 to 1 instead of 0 and like 1. See? This is Sigmoid. It goes from 0 to 1, and 10 goes from -1 to 1, and it's more inclined. It's more steep. Okay. This works well as well. And this is something that I like a lot, Swish. It was developed by Google. It's seen as the next ReLU, and then you will see why, because remember that ReLU over here is flat. Again, this allows for a little bit of minus thing, and also it's not as linear as ReLU here. ReLU went, how to say, here, and see that is a little bit more, how would I say it, elegant. Very few softwares still have it. I know TF-Learn definitely doesn't have it. So, and it's kind of interesting because this is actually ReLU multiplied by next number. So, how to say, if you want to implement it, just get the code that for ReLU, find an X, multiply by that number, and then you got your equation there. Finally, one that very people even forget that it exists, called TopMax. TopMax is one of these ones that people, again, they forget how important it is, because it's only used for the last layer. This is very important to understand. You don't use all these thingies in the last output layer. You always use TopMax. I'm not gonna get into much detail for it because, frankly, I never understood it very well, and because either way you will yes or yes use it. So you're not gonna get away from in the middle layers, in the hidden layers, you can choose any of them, but at the last layer, you will use TopMax. So end of story. Now we spoke about backpropagation, and remember that in the last video we talked about gradient descent, and then remember that I said that it's like someone skiing and then going back and forth trying until reaches the bottom of the hill. Well, that's stochastic gradient descent. And then and which is actually one of the methods that we use for backpropagation. So remember that when I mentioned that stochastic gradient descent, I said that we will study later. Well, I hold to my promise, and here we are. So backpropagation, nobody knows exactly who invented it, but it was made famous, I guess, by this guy, this Geoffrey guy, who is a professor emeritus at the University of Toronto and a Google researcher. However, even he says that he doesn't see this backpropagation as a definite answer. And he says that neural networks, in order to become intelligent of their own, we need to, he says, I suspect that means getting rid of backpropagation. Again, how does backpropagation works? Basically, here, works on the wave. Here's fast feed forward, you get the input, you pass it along all the layers until you get an output. Backpropagation gets the result, compares to what's expected, and goes back all the way, updating the weights and the bytes. So at the end, this works like a tennis match. Data goes forward, backpropagation sends it backwards, and say it's like a ball going back and forth. However, with activation functions and with backpropagation in general, we have a thing called vanishing exploding gradients. Basically, a vanishing gradient is when we go back with backpropagation, and as we go deep back through each one of the layers until we reach the beginning of the network, we finally find that the numbers, they just went to zero. So backpropagation goes each one of the steps all the way, each one of the layers all the way back to the beginning, and by the end, most likely the weights are zero. So basically, that's a non-functional neuron. So we have a problem there, and the opposite is exploding gradient, in which same thing happens, but instead of going to zero, it goes to 1 trillion or whatever. The end result is when you're training, instead of seeing waves, you see none. You start seeing a bunch of none. In my next video, hopefully we'll be able to reproduce that, and you will see that all of a sudden you get none. Okay, that happens when you have many layers. So you definitely will have vanishing and exploding gradient problems if you put too many layers. So you don't want to. The more layers you put, the more problem of this vanishing and exploding gradient you will have. Let me see if I actually put it. Okay, I didn't mention this at the time because I had not explained this. But for example, Sigmoid has both a vanishing and exploding gradient problem. Again, even though it's mentioned here, I didn't explain it, so I'm now saying what it is. So ReLU doesn't have that problem, but has another called that ReLU. Tan also has the vanishing gradient problem, just like sigmoid. I don't know if Swish has it, because this is so new that maybe it hasn't been tried. And well, this doesn't have this problem because it's just at the end. And then, so within this backpropagation things, we have optimizers, which is, it's a corny name of saying different ways of different algorithms for backpropagation. The first is SGD, stochastic gradient descent. We already studied that. That's the most known. Then the other is NAG, Nesterov accelerated gradient. It's better than SGG because remember that we made the comparison with any skier trying to reach the bottom of a hill. With Nesterov, it's like the skier knowing, I'm reaching the bottom, so I will try to slow down so I don't pass at 200 miles per hour at the bottom, and then otherwise I will keep going back and forth until I finally reach it. So Nesterov is a little bit smarter. And finally Adam, which is adaptive moment estimation, and then by far the best. Everyone uses it. Again, heroin. You go Adam, you will never want anything else anymore, and you will see why. Okay. Let's see if I can. Okay, this is a simulation, but it's actually very interesting. We have SGD, momentum, these are two that we didn't study, and we have Adam. So for our practical purposes, let's concentrate on SGD and Adam. And then we'll see which one. The idea is to see which one goes faster, most likely to this thing. So we put see that this red thing takes a long time, and the Adam is the green thing. Okay, so pay attention to the green thing and the black thing. See how fast. See how fast Adam goes. See, I mean, that's why I told you. Once you go Adam, you never were like, what? Forget it. I'm not gonna even try anything else. So at the end, they seem to all be able to get, but some are faster than the others, and some actually may take on a different turn. So again, once you go Adam, you never go back. Okay, so now we have an alternative to backpropagation, which is called genetic algorithm. This is really new stuff, and believe me, this will make you look good in your company if you're able to understand this. And thank you, you're welcome that I'm actually explaining this thing. So backpropagation is something that, how to say, even the inventor, not the inventor again, the guy who made it famous, sees as a past thing. The alternative for this is, many people say, genetic algorithms. Now, I'm a biologist, so in genetics we study that it depends on three things: recombination, mutation, and natural selection. How does it work? You got two cells. They exchange DNA, that's recombination, and then they create a third cell with a chunk of DNA from each side. That's how actually, when you dad and mom, you may be blonde like your mom, but you may be fat like your dad or something. So that's why you share traits from daddy and mommy, okay, thanks to recombination. Mutation is when you have, because of I don't know, smoking or something, or you take too much sunlight, a random piece of some DNA in your cell gets changed. And natural selection is basically when nature says, hey, this new change actually is pretty good. So for example, in this new change, you all of a sudden have 4 arms or something like that. Okay, and then you can pick up things twice as fast as the other people. You have an advantage. You look like shit, but at the end, at least you can do things faster than other people. So that's an advantage. Okay. So natural selection determines that if that new thing through a recombination and mostly mutation will be of any good, or no, it could happen that you are born without a mouth that you can eat, and you starve to death. And so natural selection plays a part there in just erasing you from the gene pool because you were born with something that is no good. Okay. So making a comparison, suppose you have a list of cities a salesman has to visit in order to sell his stuff. So this is a common problem. Then we have making a comparison with this genetic thing. We got 2 possible city lists. Okay, we grab chunks of each other to create a 3rd list. That would be the recombination thing. We create some bullshit mutation on that list. That would be the mutation thing, and then we feed it to the model to see if that thing is any good. So Mother Nature is basically us. We decide, hey, this list of cities makes a lot of sense. This guy will be able to reach as many cities as possible. And no, this makes no sense. He will spend a lot of time and a lot of gasoline, petrol to go sell among all these cities to sell his stuff. However, very important, we still need to tweak things like crossover chance, mutation chance, etc., just like we do with backpropagation. Okay, so we are still stuck with this hyperparameter and feature engineering, tuning, etc. Remember feature engineering? That's when you take all the important variables in this data set, and then and those are parameters are all the things that are related to the data set, such as the weight, the bias, etc. that we saw. Hyperparameters are things that are mostly related to the model in general, such as the number of trees in a random forest. Okay, or for example, these things too. So in this hyperparameter optimization is an automatic way of trying to find this, and we find tools such as Amazon SageMaker, Azure Machine Learning, Google Cloud. My favorite is this thing called driverless AI by this company called H2O. Driverless AI is great. I mean, you feed it a data set, somehow it is able to do this feature engineering by saying, listen, I gathered that from this data set, this and these variables are the most important. You agree with me? Most likely you will say yes. And then later he says, listen, I think that you should be doing this particular model using these hyperparameters. You agree with me? Yeah, just do your thing. And then at the end, it's really great. You just press yes, several times, and you do it and then you get all kinds of results, and you choose the result that is best for you. As simple as that. So once again, thank you for for being able to put up with me all this time. I hope you're enjoying these lessons. And in the last one, we will go through a step-by-step thing of identification of a model, okay, of something, some product or something. Okay. See, yup.